University, and she co-directs the Reasoning and Learning Lab and head the Montreal office of DeepMind in parallel. She specializes in reinforcement learning with a particular emphasis on application of AI that have a significant social impact, such as healthcare. She is particularly interested in machine decision-making in an environment when uncertainty is high. A senior fellow of the Canadian Institute for Advanced Research, a CIFAR, and a fellow of the Association for the Advancement of Artificial Intelligence, Precup has made significant contributions to AI, including the options framework for temporal abstraction. She's also a co-founder of the AI for Good Lab, promoting diversity in AI, and has received numerous accolades, including a Royal Society of Canada Fellowship in 2022. So Doina is a very busy person. So it's a real treat to have her in person present this morning. So thanks so much for joining us, and the floor is yours.
Thank you very much. I'm really happy to be here. And thank you very much to the organizers for the invitation and also for putting together a really fabulous program. I've enjoyed this morning, and I look forward to the rest of the talks as well. So I will talk to you a little bit about continual reinforcement learning, and there's a long list of acknowledgements there. Some of them are long-term collaborators, and some of them are current students who have sort of carried out a lot of this work. So since this is a fairly diverse crowd, I'm just going to do a very quick framing. What's reinforcement learning? It's about learning from interaction in the service of achieving goals. Okay? So that's the way that I think about it. And part of the appeal, as Rich Sutton has said, is that reinforcement learning really is, in a sense, the whole AI problem in a microcosm. Right, and a lot of the inspiration for reinforcement learning methods has come from animal learning theory and neuroscience. You have this little picture of a mouse there that's supposed to learn how to press a sequence of levers, and if it does the right thing, then it gets a food pellet as a reward. And so we can train biological organisms to perform tasks, sometimes quite complex tasks, by using rewards. And we mimic this in artificial agents by thinking of an agent that's embedded in an environment, receives observations, carries out actions, and receives numerical rewards that capture the goal of the task. And so we think of goals here as expressed through rewards, and the goal of the agent is to maximize the expected reward received over time. Now, there's been a lot of complex tasks that RL agents have been trained to solve. A lot of them have been games, Go, StarCraft there. On the bottom, you see some Android games. This is an environment that my team at DeepMind has put out that's a simulation environment for agents that want to train to achieve tasks on the phone. Some of these tasks are games. Some of these tasks are sort of interaction tasks. And there's a lot of actually also real complex tasks that RL agents have been trained to do. So these are two of my favorite examples. On the far side there, you have a task where you have to control these balloons that go up in the stratosphere and circumnavigate the globe, trying to provide Wi-Fi, stable Wi-Fi to regions where you can't really put cable, like, for example, in high altitude or more deserted regions. And so that was work of my colleagues, Mark Belmar, Pablo Castro, and others at Google DeepMind in Montreal. And these balloons are trained by looking at the simulator where one can sort of run lots and lots of trials, and then you learn a way to control the altitude, and then you can deploy that on a physical balloon that actually goes and flies in the atmosphere. And the balloon continues to learn online as the experience comes in and adapt to the particularities of the winds and the currents, the air currents that are available. The other example over there is from colleagues at Google DeepMind London, and it's a Nature paper from 2022 where reinforcement learning is used to control the shape of plasma inside a reactor. It's a collaboration that's ongoing with EPFL, and where we are really trying to take reinforcement learning ideas and try to tackle this task that is both really important for our energy future, but also a task where we actually have no idea how to do it, ourselves. So it's not like we can take, let's say, supervised data and then try to learn a policy by mimicking that data. There really is no expert, and there isn't any artificial system or robot or anything that people have designed that's actually good at this. And it turns out that we can train agents, again, in simulation with reinforcement learning to do this kind of complex task and then take that policy and deploy it on an actual physical device, and it does pretty well. Now, these are all exciting. There's a lot of other kinds of applications, for example, in drug discovery, adaptive treatment design, more recently, reinforcement learning from human feedback, which is quite crucial to making LLMs work. But all of these tasks pretty much are circumscribed and well specified, okay? What do I mean by that? You know, the agent that flies balloons only knows to fly balloons, right? Or an agent that plays the game of Go only knows how to play Go. And moreover, in all of these tasks, we have access to lots of data, typically by simulation, okay? So here, even in the fusion case, we have really good simulators. People have invested a lot of effort in building them. They're not perfect, but we can get lots of data through that simulation. In our LHF, we don't have as many simulators, but we have access to people, right, and people data, and so still we have plentiful of data. Now, I'm very interested in how biological systems learn. I'm not a neuroscientist, I'm not a cognitive scientist, it's just sort of personal interest. It's what brought me sort of into this area of learning. And I'm also interested in understanding why our agents, which can be very smart, much smarter than us in very specific ways, actually can't do things like we do, okay? Both from the point of view of being very general, being able to tackle a lot of kinds of situations, and also being more efficient in terms of the data and the compute that they use. So I'm interested in lifelike scenarios, and one thing that you notice if you think a little bit about agents in lifelike scenarios is that the setup is very different from having a simulation with plentiful of data and where an agent has plenty resources to compute with, right? The situation is more like the picture here where you have a very, very tiny agent in the middle of that photo that's in a very big environment. This environment is complicated, might have actually other agents in it. And the task is a lot less specified, right? The reward signal might not be so clear, the circumstances of the agent change, and the agent has to adapt, right, to the stuff that comes its way. So we have a lot less data, and we have typically one trajectory, one lifetime in which to learn. Now, yes, we can learn from other agents, we can sort of bring in other sources of knowledge, but still the information that we have access to is a lot less than in typical RL tasks. And so that's the view that I'm going to take today. We have agents that are much smaller than their environment. They have one stream of experience. That stream of experience consists of observations, actions, and rewards, like in normal reinforcement learning. But that one stream of experience has to support all of the learning processes. And the agent can't compute arbitrarily fast. It cannot remember all of the relevant experience that it has. So it has sort of capacity limitations, like a finite buffer, for example, and cannot necessarily come back to situations that it's seen before, okay? So some of the notions that are very ingrained in reinforcement learning, like, for example, recurrence or resetting to particular states or so on, are not necessarily realistic in these kinds of scenarios. Another interesting aspect is that we have a sort of speed difference between the world and the agent. The world has its own clock, moves at its own speed. The agent has some kind of time scale at which it perceives and acts and learns, and that depends on its architecture. And the agent can also perhaps choose the time scale at which it should update its representation, but these two things are not synchronized. And for those of you who are in reinforcement learning, it's actually kind of a departure from the typical sort of textbook description where we say there's a time clock, the time ticks, the agent does an action, the environment does one step, and so on. Actually, the agent and the environment are just sort of going on in parallel. And finally, the agent really has to take the experience that's coming in online and learn as much as possible from this experience. So we're going to take this sort of small agent perspective, not necessarily think about recurrence. We're going to think about the agent doing as well as possible along its current trajectory. And in order to do this, agents must construct some representation, some form of knowledge that allow quick generalization, okay? Either immediately in new situations or with just a few samples, with a little bit of experience. And this representation is going to have to be lossy or imperfect, okay? Because the agent is limited in terms of its capacity. So now the question becomes, how can we do this, okay? And what do we keep from sort of traditional reinforcement learning? What do we have to change? And really, if you think about the history of the reinforcement learning field, there's been an evolution of ideas, so this is not such an unnatural step. Initially, people thought about finding optimal policies in an environment where we know everything about the reward and the transition structure of the environment, and we can use things like dynamic programming methods, which were very popular in the 50s. And then in reinforcement learning, actually, one of the big innovations was the focus not on all the states that are possible in the environment, but just the states that an agent encounters during its lifetime. So for example, in the game of Go, if we were to think about all the possible configurations of a Go board, that's an astronomically large number. We don't get anywhere, right? But just a fraction of these possible configurations occur in real games, and we only want an agent that does well in those configurations that actually occur in real games. And so we just want to take this one step further and think about the agent doing well, not necessarily just in the states that it's encountered so far, but in the future, right? And so the goal is to do well as possible in the future, but not necessarily optimally, right? And optimality, which is again also a tenet of reinforcement learning that's been kind of baked into a lot of our theory, is actually quite relative, okay? So I don't know how many of you have kids, but at some point I had young kids at home and they were learning to cook. And the first time that my daughter cooked that omelet, it was pretty terrible, and I was still very excited, and I gave lots of positive feedback on it, because just a new thing, right? And compared to the amount of data and the amount of experience that she had and the motor skills at the time, it was actually pretty good, okay? But if I would have gotten the same artifact in a restaurant downtown Montreal, I would have been quite unhappy. So there's no such thing as optimal, really. It's relative. It's relative to the amount of data that the agent has had and relative to the state of knowledge that the agent has. Now, when we think about these agents, there are a few algorithmic properties that we want to establish. One which has been studied quite a lot, and there's a lot of actually really interesting work coming out at the moment, is stability and plasticity. So this means, how does the agent decide what to retain from the information that it's seen before, that's stability, and how much is it able to still learn in the future, that's plasticity. I'm not going to focus on that because there's actually, like I said, quite an interesting landscape of work that's not necessarily, we don't have time really to review all of that here. A second important aspect is scalability, and this goes back to the bitter lesson that was mentioned this morning, Rich Sutton's bitter lesson. If an agent has more data and more compute available, its performance should go up. So the agent needs to be able to leverage these extra resources in a graceful way. Similarly, we want these agents to have graceful degradation. So if they see a data distribution in the future that is completely different from the past, it's okay for them to be bad at it. But if the data distribution is just a little bit different, we would like the performance to still be quite good. And then finally, maybe the last point is a little bit more debatable, but again, for people who have kids, it's probably important, right? Is self-reliance. We do not want these agents to depend on us in order to learn and to do well. We want them to get their own resources and do well on their own, okay? You have a limited amount of time, you barely have time to babysit your kids, you can't also babysit your AI agents, okay? So what I'm going to talk about is some algorithmic ideas that pertain to the top three things, but especially sort of scalability, graceful degradation, and a little bit on stability and plasticity, okay? Basically, what I want to tell you about is some ways in which an agent can take its one stream of experience and use it to learn about many different things, little pieces of knowledge, and then decide which ones to retain out of this. Now, what are these pieces of knowledge? Some of it is procedural knowledge, so it can be things like partial policies, ways of acting to achieve certain sub-goals. In hierarchical reinforcement learning, we call these options. And some of them are predictive models. Okay, predictive models basically say, what is the environment response going to be to an action that's carried out in a particular situation? And so especially I want to focus in this talk on models, and in particular on building and reasoning with partial models of the environment. Now, model-based reinforcement learning actually has a long history in the field, okay? So if you have an agent that's embedded in an environment, it's getting a stream of experience, the most typical sort of reinforcement learning approach is to take that experience and put it directly into a policy. That's called model-free learning. You take observations, actions, and rewards, you crank your favorite RL algorithm, and out comes a policy, a way of behaving, and a value function that's telling you what's the estimated value of different states. However, that is sort of extracting a very little bit of information out of what is a very precious stream of data, especially if you have just one stream. A different thing that you could do is to try and learn a model of how the environment acts in response to your actions, and then that model can be used to simulate more experience, right? It can be used for the agent to replay various situations in its head, and then learn from that data as well. Sometimes people call this a world model. Back in my day, we were less ambitious, we just called it a model. It's typically a sampling model, so it's somewhere where I can put in an observation, imagine an observation, put in an action, and get out an observation and response, and possibly an imagined reward. And so back in 1990, this algorithm called Doina was proposed. It was sort of the first kind of incremental model-based RL algorithm where when we learn the model, we're going to sample it and then carry out reinforcement learning on the sample data as if it were real. And any kind of RL algorithm can be sort of dropped in there, temporal difference learning, Q-learning, anything you want. The other interesting thing about this is that here, the planning or the thinking with the model and the execution of actions are going in two parallel streams. They're not synchronized necessarily, right? Computation with the model can go in the background, and every so often when we have updates, those updates kind of percolate into the policy and affect the way that the agent is choosing actions, but the agent doesn't have to block in order to think, and that's interesting. Now, there's been a lot of work in neuroscience that was very much focused on deciding whether the brain does model-based or model-free, or both kinds of things. There's been specifically this paper by Nathaniel Doe and lots of follow-up work about the dorsolateral striatum and the ventral striatum and what's going on there. I'm not really going to talk about any of that, but I do want to tell you about models and how we make models sort of work as we would like, okay, in a better way. For a long time, one of the frustrations in reinforcement learning was that algorithms that tried to learn models were actually never really better than algorithms that tried to directly learn a policy or a value function. Wasn't exactly clear why, but one of the interesting developments in the last few years has been this idea of giving up the very high goal of modeling everything about an agent's environment and instead trying to focus the model somehow on something that matters, okay? Now, the most important thing that matters in RL is performance, okay, specifically the goal of the agent. And so this work called mu0 by Julian Schüttritzer and others at Google DeepMind, published in 2020, focuses on predicting the aspects of the environment that are important for the value function and for the policy, okay? And so the basic idea here is that you have, for example, in the case of the game of Go, you have an observation. That observation is being encoded in some kind of latent state or model state, and this model state is asked to make sure that the prediction of the value function, the prediction of the immediate reward, and the prediction of the action that would be a good action are accurate. So not necessarily to predict what the next go board is going to be, but predict, are you going to win from this position, okay? Or which move should you do? Now, how do you know what's the right move to do? One way to understand that is by doing search, okay? And this is a game where there's a simulation, so you can start at a particular state, you can do some searches, you can see with that extra computation what's the result that you get. That will inform your action choice, and so now you're going to train the model to try to correctly anticipate what would be the result of the search. And so this type of model, we call them value equivalent models. Okay, why? Because what they try to predict is stuff around the value function, which tells us the expected return. The policy is just sort of a side effect of the value function. They don't try to maximize the likelihood of the entire data set that we see. And so that's very important because it focuses the model on the stuff that matters, on the task. And in fact, mu0 was the first model-based RL algorithm that exceeded model-free agents. And this was across several tasks here. You see chess, shogi, and Go, and some Atari games. And the red horizontal lines are at the time the best model-free RL agent. And this was very exciting for people like me who believe in models. Because it was the first time that we could actually see the performance being exceeded. Now, in this particular case, we still are very focused on the value function, and we're not trying to do anything more drastic than that in terms of just remembering very partial aspects of the environment. Okay? So what I want to talk about today is something called partial models. Okay? Now, what's a partial model? Partial model has two features. First of all, it only applies in specific circumstances. And second of all, it does not predict everything. It only predicts specific features, or maybe cumulants, sometimes we call them, aspects of the environment specific to the current situation. Okay? So if I'm thirsty and I want to drink some water, I'm going to think about whether a model that predicts, picking up the bottle applies. It applies in this case because there's a bottle in front of me, so I can think about how the world would look if I would pick this up and I would take a sip of water. But I'm not predicting anything else about what's happening in this room or outside of this room or how the weather is outside. There's many, many, many aspects of the world that don't matter. Okay? Now, probably for the people who think about biological learning, this is very natural because we in our brains probably do not predict all the aspects of the world because our brains have a limited amount of energy and a limited amount of resources. But for reinforcement learning, it's actually kind of unusual because typically we think of these models as predicting everything. If we're going to think about a board game, for example, like Go, we're going to predict all of the possible next positions. If we think about the large language models, large language model would predict a distribution over all the possible next words that could be uttered in a sentence. It's not really focused. So in this example here, we have an agent that's going on a trajectory. It's building two little partial models. What that basically says, if I see a red bit in the observation and my action has a red bit that's going to flip this bit to blue, and the other one is the opposite, okay? These are very small, very specific, okay? And presumably can be acquired with very little data because they're so small and specific. The big open question is, how do we decide which ones of these to learn? Okay, and so the approach that we have been taking is basically to use the value equivalent idea in order to decide what to learn about. So I'm going to sort of tackle these two aspects separately. Learning models that apply only in specific circumstances and then learning to predict only specific features. In terms of models that don't apply everywhere, in the sort of animal learning theory literature and cognitive science literature, this is what people call affordances. Okay? Affordances arise at the interface between an agent and an environment and intuitively tell you what is possible to do. And from the point of view of model-based learning, this basically means we're not going to consider modeling aspects of the world that we cannot affect with our actions. Okay? So that's useful if you have an agent that's exploring its environment because it limits the space of actions that the agent should try. But it's also useful in terms of learning models and planning because we're only going to try and anticipate action effects. And so if an action doesn't apply in a particular situation, we're not really going to try to model it. So how do we formalize this in reinforcement learning? This was work done by my former PhD student, Kimia Ketrapal. The idea here was to think of agents as having some intent in their head. An intent can be to achieve a particular state or to, let's say, flip a feature to a different value. These intents then sort of lead to affordance relations. So an affordance relation is at the interface between an agent and its environment, and it basically states what actions apply where, okay? And apply here is taken to mean if I have an intent in mind, this action applied in this current situation is going to achieve that intent with at least some minimal probability, okay? So if I'm trying to open my car right now, there's no I can do that because I'm here and the car is somewhere else, okay? So we're not even going to try and model that action in this particular state because it doesn't sort of make sense to use resources to do that. And so you can think of these models as being maybe approximately causal because they're sort of focused so much on the action. And we can build learning and planning algorithms with these types of models. Now, how do we formalize this? The math is really not that important, but basically the way we think about it is we're only going to learn models for actions that apply in a particular situation. In other words, actions where the probability of their intent succeeding is at least some minimal amount. And now we can think about doing this not just with atomic actions in the environment, but actually also with temporally extended actions. So over there's a little picture of a task that's been used quite a bit as an example task. You have an agent that's a taxi driver. It's in a little grid world. There's passengers that come in and they have to be dropped off in one of 4 different locations. And so this taxi driver's intent is to drop off the passenger at the desired destination of this particular passenger. So that's the intent. And so now in terms of where to drive, that's sort of the option or the temporally extended action, well, the affordance is going to tell us we're only going to consider options that lead us to places that are either at the desired destination of the passenger or somewhere in the vicinity. And so that immediately sort of pares down the set of actions that we can consider, and we can learn models for these quite quickly. We can do a very simple form of planning, dynamic programming in this case. And what we observe empirically is that as we are looking at sort of fewer actions, okay, of course we can learn faster what to do. So the curve on the bottom that is going up faster is the one that has the smaller set of affordances, okay? This is some simple tasks, so all of the environments are going to learn eventually, but sort of paring down our choices both improves the speed of learning the model and also the speed of obtaining performance. Now, what happens if we also want to predict not everything about the environment, but just some aspects of the environment, okay? So we're going to focus on models that are value equivalent, so they want to be accurate in terms of the value function, but they predict partially, okay? That means they only look at a subset of features, not the entire observation. And so here's a very sort of small example. It's a mini-grid environment where you have a red agent, there's a green goal. And the agent and the goal are both on the top of that grid. And the bottom of the grid has some stuff that's moving around randomly, okay? So really, there's no point in paying any attention at all to the bottom of the grid. The agent just has to learn how to go from the start to the goal. And the sizes of these grids can be different over time. The agent has to learn a policy that's robust to that change, okay? And so we're going to impose as the goal of our model to learn in a value equivalent way, so to learn to make accurate value predictions. And a partial model would only pay attention to the top of the grid, okay? And would learn to pay attention only to the top of the grid. And so what you can see here is red is sort of a regular approach where we're learning a model that's predicting everything. Blue is the model that's only focusing on the important part of the environment, and obviously that's doing better, okay? This is a very concocted environment, so what happens if we want to do this in sort of a better and a bigger kind of task? We need to scale things up a bit, okay? And so a full sort of architecture of a model like this would be taking a raw vector of observations, in our case the image. We would take that through an encoder and we obtain a feature vector. And now for this feature vector, we're going to bring gradients from the value function, from the value estimate. The model itself is going to predict other things. Specifically, it's going to predict the immediate reward, something about the new feature vector so that we can roll the model forward, and also whether the episode is going to terminate or not. This is optional, but in our tasks, it's an important feature. But none of this is actually providing feedback back into this feature vector. Okay, so this feature vector is only trained to learn predictions that are relevant for the value function. Okay, and so that immediately sort of focuses the model on the relevant part of the image rather than trying to predict through a maximum likelihood objective what would happen everywhere. Now, what does this do? One interesting thing that we observe is that these types of models improve generalization. So here, we're looking at environments where we are varying the distractor, okay? And we're looking at the total number of steps that the agent is taking in the environment. So the faster the agent gets to the goal, the lower these curves should be, okay? And what we're doing is we are training the agent on one environment, the one on the top here, which is a 16 by 16 grid with blue balls in the bottom. And then we are transferring that knowledge into different kinds of environments, okay? Environments that have different kinds of distractors, environments that have different configuration, and so on. And these blue curves at the top here are agents that are model-based agents, but sort of trained normally, okay? The red curve here is an agent that is trained to be value equivalent. And you can see that the transfer is significantly more efficient, okay? And these agents are also responsive if transfer needs to happen in between the middle of a trial, okay? And this is basically because these models are just focus on what matters, okay? And that aspect of the environment is also, in this particular case, conveniently similar between these different conditions. Now, what happens if we try to do planning with these models? Okay, so if we try to roll the model forward in order to anticipate and then sort of back up the value function, well, regular models suffer from a problem where we cannot do many steps of planning with them. Okay, why is that? Because models have an error, and as you're doing planning, you're applying the model over and over again in sequence, that error accumulates. So even though the model could be applied, we actually need to cut things off. And so here in this sort of blue picture, models that look over 20 steps of planning are doing well. Models that look over 80 steps of planning are doing a lot more poorly because the quality of the model is not good, okay? Now, partial models can be a lot better because they're trying to solve a much simpler task. They're not trying to model all of the randomness of how these distractors are moving around. And so as we go and increase the depth of the planning, actually, the models perform in very similar ways. In order to sort of give ourselves a sanity check and try to understand how things work in a larger setup, my student, Safa, who actually just graduated recently, has started to look at environments from this ProcGen suite. So ProcGen is a set of environments that have been proposed to look at transfer learning. One of the features is that the background changes. So they're similar kinds of games, but their background changes. And so you need to have agents that are robust to that. There's some examples of these environments in the top row here. And now what we want is to understand if having these models is actually helping us to generalize in between different versions of these environments, okay? So here, blue bars are training bars. Okay, these are agents where we are actually training them and measuring performance at the end of training. The orange bars are testing bars. Okay, and here on the farther side there, you have sort of typical agents that just try to learn models that model everything. On the extreme towards me is the agent that is only focusing on modeling stuff that's relevant for the value function. Okay, so it's trained with this architecture that stops gradients from anything else. And the middle is just an ablation. And what you can see is that the gap, the generalization gap between training and evaluation is actually quite small for these kinds of agents. So again, that's sort of what we are expecting. It's an important feature of agents that must continually learn because they need to be able to apply the knowledge that they have in new circumstances. Now, that is still kind of a simple task. We want to be able to sort of further refine what it means for the model to be partial. And in order to do that, we can sort of bring in some arsenal that is currently very popular on attention. Okay? And so here, what we do is we're going to have an attention module where the agent is going to explicitly learn which parts of the image it should attend to. Okay? So this is here at the top. There's nothing really special about it. This is sort of trained by unsupervised learning. It's sort of like an autoencoder taking an image and predicting it back. But once we have the output of the attention in these attention slots, we're going to add what we call a filtration module. So what this does actually is it tries to sort of remove certain dependencies that might be specific to the geometry of this particular image. Okay? So ideally, if this is trained correctly, it's going to pay attention to certain kinds of objects in the image or certain locations in the image if that's important, but not necessarily to the exact details, right? So if an object is important, you should pay attention to the object, not necessarily the exact location of that object. And then we're going to have a sort of value equivalent simulation here, which is essentially taking our model and doing a mu0 style loop with it. Okay, so running the model forward, predicting over a long trajectory, and trying to do this computation in the agent set. And so we can look again at environments from ProgGen. I'm showing you two different games here, Coin Run and Big Fish. And at the top, you have images of the agent. At the bottom, you have where the agent is attending. Yellow means high attention. Dark is low attention. Okay. So one thing that you notice is that this agent is not really attending over fixed obstacles or things like this. Okay, at the top. And where it's attending is actually where it's going to land. Okay, which is kind of interesting. That's exactly what you should be attending to, because if you've already initiated an action, it doesn't matter where you started or where you are currently, but it does matter where you land, because that's going to tell you something about the next action. At the bottom here, this Big Fish game, the agent is this green blob. It's trying to eat things. Okay, so first it eats this red dot, and then it's going to eat this pink dot. And what you see is the agent is attending to itself and to this other agent. Okay, when the other agent has been eaten, okay, it moves on to attend to the next thing that it's interested in eating, and so on. Okay, so the attention makes sense, the outcome of it, sort of qualitatively, and is adaptive over time. Right, it's very much dependent on where this agent is. And in terms of quantitative results, the results are also quite favorable. So here we're looking at two versions of Coin Run and two versions of Big Fish. The blue lines here are model-free reinforcement learning agents, so the ones that are not particularly trained to model any aspect of the world. We have mu0 in green, which we've discussed a bit earlier. It's sort of still the state-of-art model-based agent. And then we have our two model reasoners in pink and red here with two different kinds of attention, soft attention and sort of semi-hard attention. Because we wanted to ablate that aspect. And then the orange here is an agent that has attention but doesn't sort of do this filtration step. So it doesn't try to kind of remove information that is more dependent on the particular geometry of the image. Okay? And so what you can see is that that also does quite well. It's comparable to mu0, But trying to capture this kind of invariance where we don't actually necessarily care where things are in the image, but we do care about relative positions, for example, and what the things are, that really helps. Okay. So just to sort of conclude, if you have agents that are much smaller than their environments, then there's pressure for these agents to find structure on their current trajectory, and that needs to be done continually and online and striving for gradual improvement, and that's kind of what we try to do with these agents. It's a little bit interesting to talk to my colleagues at Google about small agents, okay, because everybody's thinking about larger and larger and larger models, and that's a good point. But if you think of a world where all these large models are actually part of the world, then still one agent is quite small. Many of the ingredients that we need in order to achieve this kind of continual online gradual improvement, I think already exist, right? Some of it is in the form of these intense affordances, partial models. There's one really interesting open question, which is what should a partial model predict? So right now we rely on the value signal in order to decide what the model should predict. That's sort of in true reinforcement learning spirit. I think there's a lot of interesting possibilities here. For example, large language models might suggest to us things that are interesting to predict because they have a lot of knowledge that's already been accumulated from people or other sources. Maybe from neuroscience we can take inspiration about what the brain likes to predict, right? So I think this is a really interesting open question. There's a lot of stuff that's more sort of on the RL side, how do we formalize stuff from an empirical point of view, what kind of environments and metrics and baselines do we want? And so that's actually what I want to sort of conclude with, is this bit about evaluation, okay? So evaluation for reinforcement learning started very small with grid worlds and mountain car and very simple sort of control problems. And we've evolved it over time towards larger environments like ProgGen that I've showed you. ProgGen has a lot of noise and diversity and so on, but it's still mainly agents that are playing games, right? Even if we go to something like Minecraft, it's still sort of agents playing games in fairly circumscribed worlds. There's many more goals that the agent can achieve. There's new types of agents that might come in. But still, it's really interesting to think about, like, what would the future look like? What are interesting tasks? And this is where I also feel like this community could contribute some interesting ideas about what would be cool tasks to try. And the other aspect that's interesting is that, sort of, again, traditionally in reinforcement learning, we've been very focused on reward prediction and on the performance of the agents. I've been showing you some nice learning curves, performance curves, but there's actually many more aspects of an agent's trajectory that we should and could take a look at, right? For example, things like, is the agent generalizing out of distribution to new types of data? Can the agent do cause and effect reasoning? Can the agent compose pieces of knowledge that it has already in some kind of fast, adaptive way, and maybe even interpretability? And so we're moving more towards the direction where instead of looking at one axis, which is return, we look at these kinds of spider plots, where we have different things that we're measuring about our agents, and we try to sort of quantify them more fully. So I will stop there and happy to take any questions. Thank you.
Hi, thanks for the wonderful talk. I was wondering, so with the world modeling or modeling, you were mostly focusing on like the Doina sort of setup of really just using your model as a simulator. But another way to actually also use it is for representation learning, because you have this way more dense supervision signal that you can then harness for representations. If you now are gonna only use the value as your supervised signal, which often is very noisy or even biased if you use like Bellman errors and so on, like you lose a lot of these representation learning things. Like, I'm curious what your thoughts are on that.
Yeah, that's a great point, and I really wish we would use the models more in a more full way. So one of the things that we're exploring in sort of a different project is this idea of having general value functions. General value functions are predictions about many different things in the environment, not just the actual reward, but other kinds of cumulants or features that we may want to predict over time. And in principle, we could take those and use them to provide targets and kind of restrict the representation. So that's kind of the dream. The reality of it is that we can only make this work at the moment up to some point. So if you have, I don't know, 20 or so things that you're trying to predict in the world and you're sort of pushing those gradients into the model, that works. If you have more things that you're trying to predict in the world, it all of a sudden does not work anymore because there's too much gradient interference. And so I think that's actually a failure of our current architectures and or maybe attention mechanisms that don't sort of pick pathways that are narrow enough to avoid this process. And that's an interesting open problem. But yeah, I agree with you. That would be great to do.
Okay, no, super interesting pointer. Thanks.
Yes, I just trying to extend this analogy. You are focusing on aspects of the world, but in terms of knowledge organization, you could extend it and like think about organizing your knowledge and focusing on aspects of the models and attention between models. Like, what do you think about this direction?
I think that would be super interesting. So if you had multiple models, you could absolutely have something about attending to specific models. Affordances is a very small step in that direction because it does help you sort of attend to maybe models for actions that are applicable right now. But in general, one can imagine attention mechanisms that are more hierarchical, right? That work at the level of a collection of models and sort of decide which of these models to use at the moment, which ones, maybe to not pay attention to, and so on. Again, I don't think we have good algorithms at the moment for achieving that, and hopefully in the future that will be different. But it's a really cool direction that could be pursued.
Because it like relates to continual learning and the kind of instantiating pieces of your knowledge most appropriate for current task, and trying to combine it to like bigger pieces of knowledge.
Yeah, exactly. So some of the architectures that are currently being pursued in terms of mixture of experts and sparse mixture of experts in transformers, I think would be could be used in that context potentially. Again, it's probably a matter of somebody taking the time to explore that.
Okay, thank you.
Hi, thanks for a wonderful talk. That was really, really great. I guess some of my background is studying cognitive neuroscience of learning and memory, focusing on long-term memory. And one of the, I guess, classic key concepts in explicit long-term memory is the differentiation between semantic and episodic representations in learning. So semantic being learning detached concepts of like higher level knowledge about the world that's not bound to a specific exemplar, and then episodic memory being remembering a specific time and place at which a specific event happened that has meaning or that has a lot of specificity. And I was wondering, I guess I saw with the filtration that you've implemented in your model, like how it helps to, I guess one of the mechanisms of this and how it's implemented, some of the, there's this idea of pattern completion versus pattern separation and how that maps onto hippocampal circuitry and how basically, sorry, I'm rambling, but how you have this distinction between encountering moments when things are similar enough to previous experiences that you blend it into like a generalized representation of the world versus moments at which something really sticks out and it becomes a teachable moment. And it seems like your implementation of that filter seems to tilt the scale between these two modes. And I'm wondering if it's some of those concepts, if you've toyed with it.
That's a really interesting question. And I didn't think of the filtration, to be honest, in that way. But I think that's a very interesting point. One aspect in sort of current RL and machine learning where people are thinking in terms of this kind of episodic memory versus more semantic memory is in the area of large models and in-context learning, which can be viewed more like an episodic memory versus actually making fine-tuning updates to weights. Mm-hmm. But there too, it's very much, it's not really principled what we do, to be very honest, right? Like it depends on the problem and people try things out and whatever sort of works actually sticks. I think it's true that this kind of filtration mechanism, in a way, is taking something that would normally be episodic and sort of modifying it
I think
to,
so.
to
And
move
maybe,
towards semantics.
Maybe semantic and episodic is a little bit too lofty, but like the idea of pattern separation versus pattern completion, of when to separate a representation versus when to integrate
Yeah.
it, seems to be like, it really seems to have, you've implemented something that tilts the scale, and I guess to me that's really cool.
Yeah, and I think we could explore this quite a bit more. Like right now, we sort of also, we always apply the filtration, right? So at all points in time, we look at the current observation, we go through the sole inference path. One might imagine that this sort of more abstract mechanism or more semantic mechanism goes on its own time scale and does some future predictions over time, but we have not really implemented that.
Yeah,
And my
guess one of
students
the
graduated,
key,
so.
Oh, thank you.
Sure.
Thanks so much.
Thank you.